This is the third section in the chi-squared test chapter, and we're going to be looking at testing a hypothesis. And we now know how to work out a value of x squared. So remember, we said that the easiest way to do it is to do this, and we now know how to look up chi-squared from a table, remembering that that's the number of degrees of freedom. And what we're going to be doing is we're going to be comparing these two numbers. Yeah, basically comparing. Here it's going to give us like the variance, isn't it, of our what we observe from our expected, and then this is going to give us the cutoff point where we accept or reject H0. So this is going to give us the critical value. So remember that H0 is always going to be that your observed data fits the distribution. Observed data, let me put fits or is close to expected values. Okay, so in other words, it fits the distribution. H1 is going to be that it doesn't observe data does not fit expected values. So if our chi-squared is going to give us our critical value, if our calculated value of x squared is less than our chi-squared, okay, which means basically it's less than the critical value, then we will accept H0. Okay, so we're saying that our variance of our observed data is less than the critical value. It might be worth writing down. So I'll put it in quotes. Word variance, not really variance. Variance of observed. I'll put stroke expected. So we're comparing it to our expected data or values is less than critical level or critical value. Whereas if our variance calculation, this, is greater than the critical value we get from chi-squared, then we reject H0. So it's either going to be a good fit, which is this. Our data is a good fit to the distribution or from the expected values, or it's not a good fit. So our observed values are not close to what we expect. Okay, in an experiment where a dice is rolled 120 times, the frequency distribution is to be compared to a discrete uniform distribution as shown. So I've got my observed frequencies in one row, and I've got my expected frequencies in the bottom row, and it says test at the 5% significance level whether or not the observed frequencies could be modeled by a discrete uniform distribution. So the question is basically asking, are these observed frequencies close to a discrete uniform distribution? And in a discrete uniform distribution, all expected frequencies would be the same. So all, and you can see that in the table, all expected frequencies are the same. And you can see that in the table, they are the same, yeah? So the first thing to do is to see, do we need to combine any cells? And the answer is no, because none of the expected frequencies are less than 5. So don't forget that bit. We do not need to combine any cells. So we can leave it as it is and go ahead and calculate x squared. So we need to state, if we're doing a hypothesis test, we're doing 5%, we need to write down what the null and the alternate hypothesis is. And it's pretty straightforward. It's almost like writing down what's in the question. So H0 will be that the distribution, or the observed distribution, or the observed frequencies, the observed frequencies or distribution can be modeled by a discrete uniform distribution. Whereas H1 is just basically going to be the same thing, but we just replace can with cannot. Yeah. The observed distribution cannot be modeled by a discrete uniform distribution. So it's either it can or it can't. So that's always state, any hypothesis test, always state H0 and H1. Now we're going to calculate x squared using the formula, the sum of the observed squared over the expected minus n, and we do this for each column. So I'm going to write the full calculation out. So we will have observed squared in the first column over 20 plus the next observed squared over 20, the next observed squared over 20, all over 20 because all the expecteds are 20, next observed squared over 20, next observed squared over 20, and the last observed squared over 20. Okay, so that's, you need to find the sum of those. Then we take away n, and n is going to be 120. So I will work this out and see what we get. Right, now for the bit in the brackets, we get 617 over 5 minus 120. So I will get 17 over 5, which is 3.4. Okay, so this is my calculated value of x squared. Now what we need to do, we need to compare this to chi-squared so that we can decide whether to accept or reject H0. Is that variance number 3.4? Does that mean it's close to the distribution, discrete uniform distribution, or is it too far? That's what chi-squared will tell us. So in this question, I haven't had to combine any cells. I have 1, 2, 3, 4, 5 degrees of freedom. So I could write nu equals 6 minus 1, yeah, because there's 6 cells. 5 of them can move around. The 6th one is fixed. So 5 degrees of freedom. So I'm going to be looking up chi-squared 5, and it's 5% significance. So this is where we jump to the table on page 192, which I'm going to do now, and 5, so row 5, and the column with 5% significance, and 16.750. So 16 0.750. Oh, sorry, let me correct that. I looked at the 0.5% column. I looked at the wrong column. So sorry about that. It should be 11.070. Sorry about that. 11.070. Always helps when you look at the right column in the table. Now, my value that I calculated, which was 3.4, is less than 11.070, less than my critical value. So I can say the spread is small enough for me to say that I can accept H0. And don't just say accept H0, we can say that the observed distribution, or we could say there is enough evidence to suggest that the observed distribution, let's write that down, there is significant evidence to suggest the observed distribution can be modeled by and I'll just put discrete uniform distribution only because I haven't got enough space, but obviously don't just write dud at the end of a question. Okay, Alan has two identical four-sided spinners, numbered 1 to 4, written on each of them. He carries out experiments where he spins both spinners at the same time and he adds the scores together. After 160 experiments, the frequency distributions are shown below with our observed values here and our expected values in the row below. Okay, so the expected table also shows the expected distribution of the scores if both spinners are unbiased. Test at the 2.5 significance level whether the observed frequencies could be modelled by the expected distribution shown. Right, so first thing, do we need to combine any cells? Nope, because there are no expected values less than 5, so we don't need to combine any cells. So let's start by writing out H0 and H1. So H0, now let's write this slightly differently. We could just write that the dice are not biased, which basically means that we'll get pretty close to the expected frequencies if they're not biased, because it does say that the table shows the expected scores if both spinners are unbiased. So that's going to be H0, H1. We can just write the dice are biased. Now how are we going to work that out? Well, we're going to work out this sort of variance, as I call it, which is x squared, and we're going to compare it to chi squared. So x squared using the sum of the observed squared over the expected minus n. So this is going to be 14 squared over 10 plus 11 squared over 20 plus 26 squared over 30 plus 33 squared over 40 plus 42 squared over 30 plus 18 squared over 20 minus 16 squared over 10 minus n, and n is going to be the number of experiments, n 160. So let's work this out. Right, now for the bit in the brackets, we get 21121 over 120. We need to take 160 from that, and that's 1921 over 120. So it's 16 point, and it's like 008, and then 3 recurring. Okay, so we could pretty much call it 16, couldn't we? It all depends on what we look up for chi-squared. Now, here we have 1, 2, 3, 4, 5, 6 degrees of freedom, because that last cell is going to be fixed once we know the other 6. So we'll write nu equals 1, 2, 3, 4, 5, 6, 7, 7 minus 1. So write this down to show that we've got 6 degrees of freedom. So I'm going to be looking at chi-squared with 6 degrees of freedom and 2.5% significance. So I'm going to make sure I look up the right value this time. So 2.5% is going to be this. So I need to make sure I don't look up 25% or 0.025%, something like that. So 6, row 6, and the column with 2.5%, and I see 14.449 in a table on page 192. So that is 14.449. Now we've got a spread of variance which is greater than that. So now we write that our x squared is greater than chi-squared, isn't it? So it's more spread. Yeah, or you could write out this, that 16.008 free recurring is greater than that. So this means this time that we will reject H0. It's too far away. Reject H0. So we'd write something like there is evidence or sufficient evidence to suggest the dice are biased. And I've just realized these are not dice, so wherever I put the word dice, just replace it with spinner, or we could change the question and change spinner to dice, couldn't we? So I will change this to spinner. Yeah, it helps if I do read the question. Right, we've got a school conducted a survey into the impact of a new exercise club that it was having on students. Prior to the new club starting, 60% of the students said they had no regular exercise. 30% reported, just underline this, 60% no regular exercise, 30 reported exercising once a week, 10 reported exercising more than once a week. After the new club started, they surveyed 150 students to find out how often they exercise. So this is what was observed. Yeah. Now we're going to compare this to what we expected. Now to work out the expected, we're going to do this 60%. We're going to work out 60% of 150 to work out the expected for no regular exercise. We'll work out 30% of exercising one a week to work out the expected for that, and 10% are exercising more than once a week. Now in this case, the expected is basically if there were no change. Yeah, if the club had no impact on people's exercising habits, then it would be these expected values. So that's going to have an impact on how we write H0 and H1. So in this case, the expected values are going to be what it was before the new club opened. So as if there was no impact or on people's exercising habits. So what I'm going to do is I'm not going to draw the table out again. I'm just going to write the expected down here and try and extend that table. I'm having trouble writing the word expected. There we go. So basically the rest of the table is going to come down here. The total is still going to be 150. So this value here is going to be 60%, no regular exercise. This is going to be 60% of 150. So if we work that out, we get 90. This value here, let's just do this, is going to be the one in green, 30% of 150. So that's going to be half of 90, 45. Then the last one we've got is more than once a week. That was 10%. So 10% of 150. And that's going to be 15. Now we're ready for H0 and H1. Now H0 is always based on the expected. Now the expected might be that, you know, it's not biased because we've got the expected frequencies here. The expected values were the values based on the people doing exercise before the club opened. So H0 is going to be that the new exercise club has had no impact on how often people exercised. You could word it differently to that if you want, but that's the gist of it. We want to write. And H1, that the new club has impacted people's exercising habits or how often they exercise. So first thing we need to do is to work out x squared. So before we do that, actually, we need to look at the cells, look at the expected values. Have we got any expected values less than 5 that we need to combine? No. So I can work out the number of degrees of freedom since I've got 3 cells. Let's write this down in black. So since we've got 3 cells and 1 has to be fixed, we have 2 degrees of freedom. So we'll use that in a moment. So now we're going to do the sum of the observed squared over the expected minus n. So the observed 73 squared over 90 plus 57 squared over 45 plus 20 squared over 15 minus the number of observations, which was 150. So we get 14227 over 90 minus 150. So if we do that, we will get 727 over 90, which is 8.0, and it's like 7 recurring. Okay, that's what it looks like on my calculator. So we could call it 8.08 or 8.078 if you're rounding it to 3 decimal places, but that's fine as we are. So now we're going to work out or use the table to find chi squared. Now with 2 degrees of freedom and 5% significant level, so we either look in our formula book on page 36 or go to page 192, making sure we're looking at the 5%, not the 0.5% as I did, and we're only the second row down. and I'll get a value of 5.991 from the table. Okay, so equals 5.991. So how does our spread compare? Well, our observed spread, our observed variance, is greater than chi-squared with 2 degrees of freedom, or you could write it as 8.07 is greater than 5.991. So whenever our x squared is greater than chi-squared, that means that it's too far away from what we expect, so we reject H0. Now rejecting H0 means that the exercise club had no impact. In this case, rejecting H0 means that the new club has, or there is evidence, so we should do that rather than it's definite. There is evidence to suggest the new club, and you can just use the wording in the question, the new club, because they talk about exercising habits, has changed attitudes to exercising. And I'd probably suggest to use exactly the same wording in the question, because the word in the question was about, is there evidence? So basically your answering that question, is there evidence? Yes there is, or no there isn't, and use the wording that's been given there. That's the best way to do it. Right, you should now be able to do exercise 6C on pages 102 to 103. So just as a quick recap, when we do these questions, you are going to calculate x squared, and I would use this formula here. That's a quick way of doing it. But remember about combining any cells, combining any cells where your expected is less than 5, and you want to combine them so that you end up with expected cells or expected frequencies greater than 5. And then you'll use the tables to look up chi-squared. Now remember, the degrees of freedom you get from the number of cells after combining. Number of cells, let's write it properly. Number of cells after combining -1, and then we'll compare x squared to chi-squared with our number of degrees of freedom. If it's greater, we reject H0, it's too far spread away from what we expect. If it's less than that, we'll say, right, the spread, the variance is small enough for us to not be concerned. We would accept H0, and that's always going to be the case with these hypothesis testing questions where we are using the chi-squared distribution.